Welcome to Learn Extra. Today we're doing a second session on our trig ratios, and you have already learned how to use the primary ratios. So let's talk about it. So it's defining ratios in the Cartesian plane. Well, previously you've actually worked with this, but you've always worked with it in triangles. So what we're doing now is we're saying, okay, that's all very well if we're working in a triangle, but we need to be able to define it within a Cartesian plane, and of course your Cartesian plane is your x and y axis. So we need to transfer what we've learned here onto here, and in particular we have to work with our reciprocals. Right, so let's move on to the next slide, and as you can see there it says defining ratios in the Cartesian plane, and our key focus is of course the trig ratios, and especially, as I said, the reciprocals, because up to now you know about sine, cos and tan, but we need to also learn about their reciprocals, which are cosec, sec and cot, but I will explain that a little bit more. I've mentioned the Cartesian plane, and then of course out of that comes something called the cast diagram, which I'll talk to you about, and the special angles of 0 and 90 degrees. You have learned how to use special angles of 30, 45 and 60, so this now just completes the set of special angles with 0 and 90. Okay, so let's start over here with what you know. Remember how we learned it? We started off with a right angle triangle, and we said if this is my angle theta, then the side opposite the angle I'm interested in is called the opposite. As I can say, you can always laugh at mathematicians because we always make it very simple for you. We use the obvious. And then of course opposite the right angles we call it the hypotenuse. And remember, hypotenuse is always the one that goes opposite the largest angle. And then the remaining side is called the adjacent, and of course adjacent makes sense because the adjacent is the one alongside. So if you look over here on the drawing, the hypotenuse is there, alongside is the adjacent. So that's how we got the names of this, and our definition said that sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. Now I like to remember it, and I'm sure the presenter who did this first bit with you taught you little rhymes to help you remember these things. I always go, some old hens cackle and howl till old age. So that gives it to me. Then I know that sine is going to be the opposite over the hypotenuse, cosine is going to be the adjacent over the hypotenuse, and tan is going to be the opposite over the adjacent. Now we are going to define the reciprocals, and I'm going to add to this drawing the three ratios that match in as a reciprocal. But before we do that, what is a reciprocal? Well, let's think about it. If I say to you the number 2, what would be the reciprocal of 2? Well, if you remember back to when you were in probably grade 8 or 9, they talked about the properties of 1. And they said if you times any number by its reciprocal, you get 1. Let's write it down. So 2 times what equals 1. Well, the only way for that to happen is to think to yourself, well, 2 is a whole number, so we can put it over 1. So to get it to actually, in effect, divide out, I need to times by the inverted form of that, so it'll become a half. So now if I do that, that will divide into there, and you can see I get the 1. So if I had a half, what would the reciprocal of a half be? Well, if it's a half, I would turn it upside down, so it would be times 2 over 1. And again, you can see if I do that, I'll get 1. So that's what we mean by a reciprocal. So if we are looking then at these ratios, and I'm talking about the sine being opposite over hypotenuse, the reciprocal would be hypotenuse over opposite, and that means I must define a new ratio. Likewise over here, this would be hypotenuse over adjacent, and I need to define a new ratio, and over here I would change it to adjacent over opposite and define a new ratio. So that's what our actual main drive of this lesson's about, is introducing you to these three reciprocals and getting you to use them. And they're not a huge stretch. They are very much along the same lines as what you've learned with the three primary identities, or rather ratios. Right, so let's go to the next slide. Right, the next slide, as I said to you, is called the reciprocals, and this is where we start giving the names. Now remember I said to you that we want the reciprocal of sine. Now if the reciprocal of sine, we must times by 1 over sine so that we get the answer 1. So this is saying on the slide 1 over sine theta is equal to cosec theta. Now the proper name of cosec is cosecant. Now you can see that normally what we do is we take the first 3. But if we did the first 3 here, we would get cos, which we've already defined. So that's why they use those 5 letters to get cosec theta. Now, of course, secant is the next one, which is the reciprocal of cos. And again, we can go back to our using the first 3 because we don't have a ratio called sec. Right, now cot, if we go to cot, the proper name for it is cotangent. Okay, you can see the tan coming out of it here, but again, we name it with the first 3 letters. Okay, so over here you can see cosec is defined as hypotenuse over opposite, sec is defined as hypotenuse over adjacent, and cot is defined as adjacent over opposite. So what does that mean? That means if I take tan theta and I multiply it by, say, cot theta, because those two are reciprocals, I must get the answer 1. Let's try it out. What was the definition of tan theta? Well, the definition of tan theta is opposite over adjacent. So it would be the opposite over the adjacent. And we have just defined our cot to be adjacent over opposite. And the moment I do that, let's find ourselves another color. The opposite will divide into the opposite, and the adjacent will divide into the adjacent, and the answer would be 1, which would then prove that these two are actually reciprocals. Now, you'll say to yourself, well, how am I going to remember this easily? Well, remember that little drawing I put up earlier on, where I said to you, let's do shield your, sorry, I nearly used the wrong definition. Let's just go back here. We're still using some old hens cackle and howl till old age. So your sine is opposite over hypotenuse, your cos is adjacent over hypotenuse, and your tan is opposite over adjacent. Right, so tan's reciprocal was cot. Now, what you've got to remember is the s's do not go together. So there the sec will come in, and over here the cosec will come in. So they go with the opposite one. Now, when I read the originals, I will read down. But when I read the reciprocals, I will read up. So when I want cosec, I'll say hypotenuse over opposite. So this little table is quite a useful thing to put in on your exam paper immediately as you get in, or your test paper. So as you get in, you put it alongside there, some old hens cackle and howl till old age. Then you put in your reciprocals, cosec, sec, and cot at the bottom. And then you just remember that if you're reading the original, you read down, and if you're reading the reciprocal, you read up. Okay, so that makes it easier for you to remember. Right, let's see what the next slide has. Now, what we're going to do is we're going to play with the concept of deriving a reciprocal ratio. And I've got a triangle here, and the question asks me to find the cosec of A. Now remember, the first thing we do on triangles is we name the triangle according to the angle we are working with. So we are working with angle A. So I go to my drawing, there's my angle A, and the first thing I'm going to do is I'm going to name all the sides using A as the reference point. So if I'm using A as the reference point, the opposite side will be this one. So I always fill the opposite in first. Then I know opposite the right angle is the hypotenuse, because the right angle will be our largest angle in an acute angle triangle. And then the remaining one must be the adjacent side. So we would name it just like we did for the primary ratios. And now we go along and we say we want the cosec of A. Now remember, cosec is your hypotenuse over your opposite, because it's the reciprocal of sine. So the hypotenuse is going to be AC, and your opposite is going to be BC. So that would be how we get that, no problem at all. So it's up to you how you name it. By the way, one more thing I'd like to mention while we're here, there is another way to name sides. And while we're doing it, let's just mention it. If this is vertex A, we can call this side little a. If that's vertex B, we can call this side little b, and if this is vertex C, we can call this side little c. So when we refer to the sides, we use the little letters. When we refer to the angles, we use capital letters. So that just helps you if you want to name it a different way. So that means you could go along here and say it's equal to B over A. But probably that would be safer at this moment in time when we get more complicated and we start working with more variables and strange things happening in the drawing. Then it is useful to use the little a's, little b's, little c's. So certainly in grade 11, you will see a lot of that. Right, let's move to the next example. Okay, this time they're asking me to find the sec of C. So remember what we do. The first thing we do is we identify the angle we're working with. So we're working with angle C. Now we are going to name the triangle according to that angle. And remember, the first one we always do is the opposite side. So we go to C. Opposite is literally opposite, so there it is, that's our opposite. And don't be shy to write on the opposite. And what I do is I use color, because color helps me. So if I'm referring to two angles at the same time, so say I'm using the same drawing for C and A, then I would do the C in green and the A in some other color, red or whatever it might be, just so it's easy to refer to. So that's your opposite. The next one we always put in is the hypotenuse, which is the one opposite the right angle, and the remaining one is the adjacent. So if we go down here and we want the sec of C, remember sec is the reciprocal of cos, so it's hypotenuse over adjacent. Some teachers encourage you to write it in here, but I don't suggest you do, because you know it's not good maths practice to write three equal signs on the same line. It's really not advisable. So if you did that and you wrote it here, hypotenuse over adjacent equals, and then write it again, it just doesn't look good. So I would encourage you not to write more than one equal sign in a line. It just looks more professional and it looks more mathematical, so try not to do that. So your sec is your hypotenuse, which is AC, over your adjacent, which is BC. Okay, so nice and easy, and I'm sure you've got the idea of that. Let's see what the next slide has. Right, now it says, again, deriving a reciprocal ratio, and I guess you can guess what's happening. We've done a cosec and we've done a sec, so obviously our next one would be our our cot. So yes, it is, it's the cot of A. So remember, the cot is the adjacent over the opposite, because it's a reciprocal of tan. We're working with angle A, so we mark the angle A. The side opposite the A, so this one here is the opposite side. Opposite the right angle is the hypotenuse, and the remaining side is the adjacent. It's a very good practice to always do what I've just shown you, to always mark your angle and write in your opposite adjacent hypotenuse on it if it is a triangle. We're going to take you beyond that today, so you will see another use of this as well. Right, so cot, as I say, is adjacent, and the adjacent would be AB over the opposite, which is BC. And so we have the answer of that. So I'm sure at this stage you're feeling that there's nothing really different from what you learned with sine, cos, and tan. It's just that now we have different ratios. We have them turned around. But the procedure is exactly like you did the first three original ratios. Right, so let's see what we do next. Well, what we do next is we say, okay, what is wrong with what we've got before? Let's just go back to it. Well, we are in a triangle, which means it limits me to working with angles less than 90 here and here. So I'm sort of restricted. That must be 90, and these two together must add up to 90. So I really am limited in what I can do with my trigonometry if it has to be a right angle triangle. So what we need to do is we need to find a way to take it beyond that, and we do that by moving the right angle triangle onto a Cartesian plane. So let's have a look at the drawing. Right, so here's our explanation. We have the Cartesian plane, and as you look over here, you can see that in actual fact, that is the right angle triangle we were looking at. Do you agree with me? This would be the origin, and we've called this point X. Remember, that's the positive half of the X-axis. This is the negative half of the X-axis, and of course, positive half of Y, negative half of Y. So at the moment, this little figure I've got over here is exactly what I had in the previous picture, except I've taken it and lifted it and put it on a Cartesian plane. You'll say to me, well, why is that going to help me? Well, what's exciting about this is this blue line here starts to act as a kind of radius. In other words, excuse my drawing, it's not the best drawing in time, but it gives you the idea. What I'll be able to do, and I'm going to do this and see if it works, so let's see if it does. Yep, it's going to. I can detach that and move it beyond the first quadrant into the second quadrant, and we'll talk about that in a moment, and maybe even into the third, into the fourth, and back to its primary position. In other words, I am not restricted to working with angles between 0 and 90 if I can detach it like this. So all we need to do is find new names for the things we have. So let's look at our drawing. Over here we've got 2 and 3. Now, do you agree with me? This is my x value, and this is my y value. So my x value would be this measurement here. So that's my x. This yellow bit is the y value. And as I've just pointed out to you, this blue thing can be seen to be a radius. So if I look at my definition, and I say to you, what is the sine of angle A? I've called A over here. Well, it's going to be my opposite, which is y, over my hypotenuse, which is r. So in other words, what I'm doing is I'm going over here and I'm saying that would be the opposite, that would be the hypotenuse, and this would be the adjacent. And I've now given it the names x, y, and r so that I can, as I've just shown you, detach this point and rotate it around my circle. And if I now look at the cos of A, well, I know it's the adjacent over the hypotenuse, so it would be x over r. And lastly, if I look at the tan of A, it would be the opposite, which is y, over the adjacent, which is x. Which means now that I'm not tied just to angles less than 90. Because I can move it and I can get values for x, y, and r no matter where I am in the Cartesian plane. Because as soon as I know the coordinate, I can find the radius. If I know the radius and part of the coordinate, I can find the missing coordinate. So I'm always possible to work with this, given that in actual fact that's describing a circle. Right, so let's have a look and see what we've got on the next page. Well, before we go on to that, that just showed the 2 and 3. So what that would mean is that this x value is 2, and this y value is 3. And of course, can we find the radius? Yes, we can. From Pythagoras' theorem, we know that x squared plus y squared is r squared. So we would have 2 squared plus 3 squared equals r squared. So it's 4 plus 9 is r squared. And so we can say r squared is 13. So r is equal to the root of 13. So I can go over here and put in the value of that very easily, no problem at all. Right, so let's see what we can do now. So now they've given us the definitions in a new way. They say defining the trig ratios and reciprocals on the Cartesian plane, we know that sine theta is equal to y over r, which means cosec theta, which is its reciprocal, must be r over y. And if we look over here at cos theta, we can see that it's going to be x over r, as I've just shown you using the adjacent over the hypotenuse. And if I'm doing the reciprocal of that, it is r over x. And last but not least is good old tan. And if I look at tan theta, it's y over x. And if I want its reciprocal, it is x over y. Now, okay, let's talk about how we can make ourselves remember this a little bit better. Again, I would use a kind of little triangle, little gritty thing to work with. And I learn a new rhyme now. It goes as follows. It says, shield your rear, cause x rays tan your exterior. Okay, so it goes shield your rear, cause x rays tan your exterior. Right, so if we look at that, that's your sine, that's your cos, that's your tan, and of course your reciprocals are cot, sec, and cosec. And once more, the rule applies that if I'm reading cosec, I read this way, sec this way, and cot this way. But if I'm reading sine, cos, or tan, I read downwards. Right, that's a nice way to remember our ratios. And as I say, when I walk around the class, I see children using it all the time, and I giggle to myself because those rhymes are used to just get it out quickly and jot it down on the side. Anyhow, we will be with you shortly. See you after the break. Hi, welcome back. Let's carry on now and let's extend this concept we started earlier where we talked about not needing to work with angles less than 90 degrees. So what I have here is what we call the cast diagram, and quite a nice way to remember it is all, and it does help if one selects the pen, all students talk crazy. So A for all, S for student, T for talk, C for crazy, and that helps us to remember it. And I'm going to go through it in great detail with you now so that you get to understand it. So this is the first quadrant. We always start at the 0 degrees to 90 degrees and call that quadrant 1. And what's important about the first quadrant is that if we look at the x value, the y value, and the r value, we will find that the x would be positive, the y would be positive, and the r value would be positive. And in fact, I think I must rather use the blue pen. X is positive, y is positive, and r is positive. I think it shows up nicer for you. Right, so what we do is we go over here, and what we want to do is we want to pick this line up and drag it into the first quadrant somewhere. It could be anywhere here, so it could be up there, down there, but do you agree with me that what we do know is definitely this x and this y will be positive, and a radius is a length, and a length will be positive. So if x, y, and r are positive, what do we know about all our ratios? Well, let's go and have a look. Taking it down a little bit here, let's get a different color pen, and let's look at them individually. If I look at sine theta, remember it was y over r. Well, it'll be a plus over a plus, so overall a plus. Cos of theta is x over r, so it's plus over plus again, which overall is a plus. And tan theta, which is y over x, which is again a plus over a plus, so overall a plus. So before we go any further, obviously, if we're dealing with a reciprocal cosec theta, it is r over y, so it won't change the fact that it's a plus over a plus, so overall we have a plus. When I deal with the sec of theta, which is the r over the x, again it's a plus over a plus, so it's overall a plus. And then if I look at cot theta, which is defined as x over y, again it's a plus over a plus, so it's a plus. So that's why on this cast diagram we say all, which stands for all ratios are positive. Right, so that's interesting. So let's now move ourselves into the next quadrant. So I'm going to pick the line up again. If it'll let me, I've just gone off the thing there. Yes, there it is. And I'm going to rotate it through to this quadrant. Now, again, these are the coordinates x and y. But what do we know about x and y here? Well, firstly, the x value would be this one down here. And what do we know about this? This is the negative x-axis. So this would be a negative value, and y is here, so that would be a positive y value. Now remember, I said to you the radius is a length, and so it will never be negative. But let's prove it. Let's use x squared plus y squared is r squared, Pythagoras. And we know that if we take a negative, whatever it might be, and we square it, and we add to a positive and we square it, we would get a plus plus a plus, which means overall the r squared is a positive. And of course, because it's a length, I would only take the positive answer of it. So definitely, the radius will always be positive. Right, so now as I've said to you, the x is negative, the y is positive, and the radius is positive. So let's see what that does to our ratios. So let's just tidy that up a little bit. Let's take away what we had done in the previous bit there and see what happens now. Right, so let's pick another color. Let's take yellow. Now remember, I said to you the y is positive, so I'll have a positive over a positive and a positive over a positive. So both of these will give me positive answers. But cos theta is the x value, which is a negative over a positive. Now, a negative over a positive makes a negative. Sec is positive over negative, and again, a positive over a negative is a negative. So what we're finding is that this here, these are coming out negative. Let's see about tan. Well, tan is a positive y and a negative x, so overall it'll be a negative. Likewise over here, we have a negative x and a positive y, so overall a negative. So only two of the ratios, sine and its reciprocal, are positive in the second quadrant. And if you look there, we had the s. And I'm saying to you that this s stands for sine theta and its reciprocal cosec theta. Of course, with our little rhyme, we don't want to put the reciprocals in quite yet. We'd rather put those reciprocals in afterwards so it's easier to understand what's going on. Right, so we are happy so far. So let's go and move this little thingy around, and now we're rotating into the third quadrant. By the way, before I go out of the second quadrant, just one thing I want to mention. The angle I'm dealing with is in fact that whole angle there. So we've measured from the positive x-axis to the line. Okay, so let's just take off that so we don't have too much of a mess going here. And I think I need to just, yeah, well, that's fine. It's good enough. Right, let's pick this up and let's rotate it now into the third quad. Now, in the third quad, what do we know about x, y, and r? Well, as we've said, r is always positive. But what do we know about our x and our y? Well, over here, if I look down and I read off the x value, do you agree I'm reading off the negative x-axis? So the x would be negative. And if I read off the y value here on my Cartesian plane, it again will be negative. So this time r is positive, but the x is negative and the y is negative. And before we move off it, I just want to refresh your memories again. The angle I'm talking about is the angle measured from that positive x-axis all the way around to the ray that I've got over here, or the radius that I've got over there. Right, so let's go down and let's see how this is looking. Let's take this off. And, oops, that wasn't very good of me. I've just wiped out my ratios, but it's fine. We'll put them back. I'll go back to the green pen so we can write it in. So that was y over r, that was x over r, and that was y over x. Right, so let's look. We know from what we've just discovered that the y value is negative and the r value is positive. So a negative over a positive makes a negative. And of course, a positive over a negative also makes a negative. Now, if I look at x over r, it's going to be a negative over a positive again, which makes it a negative. And here I'm going to have a positive over a negative, which makes it a negative. But when I get to tan, the y is negative and the x is negative. So a negative over a negative makes a positive, and likewise a negative over a negative makes a positive. So these two ratios are the positive ones, and if we look at the little rhyme we remembered, we can see that that is going to be t for tan, and so it makes perfect sense that that's the case. So we know in that quadrant the only ones that are positive are tan and its reciprocal cot theta. Right, now we only have the fourth quadrant to go to. So we're going to rotate into the last quadrant. We're going to talk about our values of x, y, and r, but I'm sure by now you've got the idea of it. And you can see you could go and work it out literally from first principles if you wanted to. And all we're doing by giving you these rhymes and little things is to make it easier for you to remember. But you're very welcome to go back to basics and understand it from the very start. All right, so let's go over here. Let's pick up the line again and let's rotate it round to the fourth quadrant. And again, it can be anywhere in the fourth quadrant. Doesn't have to be where I put it, but that'll do. And again, if I'm talking about the angle, I'm talking about the angle all the way around to that where that ray stops. So this time it would be from the positive x-axis all the way through. So it would be greater than 270, but less than 360 degrees. Right, now what do we know about x, y, and r here? Again, r is always positive. It's a radius or a length. The x value here, if we look down, will be on the positive x-axis, so it'll be positive, and the y would be off here, so it would be negative y. So if we go down to our ratios, and again, let's just clean up a little bit. Okay, and let's do the same with this one. And Let's make it a yellow pen. Let's go through it again. So we've said the y will be negative. The radius is positive. So negative over positive makes a negative. A positive over a negative makes a negative. And over here we've got a positive over a positive. So this one is going to be a positive. Likewise, that's a positive and that's a positive. So overall we have a plus. Now we go to tan. Tan, we've got the y is negative and the x is positive, so overall a negative. And over here we've got a positive over a negative, overall a negative. So this time the ratios that are positive are cos and its reciprocal sec. And remember that was the c, which stood for cos, and its reciprocal, I better use the blue pen, sec. So that now helps me to organize myself. So what do we need to know so far? Very, very simply, we need to know the ratios in terms of x, y, and r. And secondly, we need to know when things are positive or negative. And in fact, it makes it easier to just write the ones that are positive in the quadrants, and then it's no problem, all the others are negative. So as a very quick summary, I'm going to tell you what you need to know in 2 seconds and what you should jot down on any exam paper or test you write immediately if you're doing a trig test. Right, here we go. I'm going to give you a flash survey. So over here, let's rather use another color. Let's use the yellow. Remember, I've shown you how to use this little grid. Shield your rear, cause x rays tan your exterior. And this is cot, this is sec, this is cosec, this is sine, this is cos, and this is tan. Right, so that gives me my ratios. We read this way or this way, depending which way we are. And then the last thing I need to know is that the cast diagram, all students talk crazy. Okay, all means all positive. Here only sine and cosec are positive. Here tan and cot are positive. And here cos and sec are positive. And now we're ready to work. We've actually got it all under control. That's all we need to know. Right, so let's now go and have a look at a question and see what we can do. Right, but before we do that, I'm going to just stop for a few seconds and talk about your special angles. You remember at the beginning I said to you, we're going to talk about special angles of 0 and 90 degrees. Now that's in light of the fact that we now have a Cartesian plane to explain it. So if we're looking at our axis, let me just pop it down here. Yeah, it should be fine in pink. Over here. And this is my x-axis, this is my y-axis. We know that on this coordinate here, this is where 0 degrees is. The x value will exist, but what do we know about the y value? The y value will be 0. Likewise over here, on this axis, where it's 90 degrees, we know that the x is 0 and the y will exist, whatever the y may be. So if I'm talking about the sine of 0 degrees, as we know, the sine of 0 is opposite over hypotenuse, but in terms of what we've just been working with, it is your y over your r. Now you see here I am an example of where it's not very nice to have this like shade thing going, so I'm going to rather write it at the bottom here. So the y value at 0 degrees would be 0, and the r value doesn't really matter what it is. What do we know if we're dividing r into 0? We know we're going to get the answer 0. So the sine of 0 degrees is 0, and we can just learn that. Later on you will learn to do trig graphs, and when you learn trig graphs you'll understand why that is the case as well. But I think this is a good explanation to start you off. Right, now we go to the cos of 90 degrees. Now if we go over here to 90 degrees, it's up there. And as I said to you earlier on, it's adjacent over hypotenuse, so let's move it into what we know it as. We know it as x over r. So if I do that, the x value here is 0, and the r value is still r. What do we know about anything divided into 0? The answer is 0. So what I've concluded is that the sine of 0 degrees is 0, and the cos of 90 degrees is 0. Okay, so that's useful to know. But now we come to our friend tan theta. Tan theta is interesting because it makes your life ever so more complicated. So let's talk about it. Let's put back our axis over here. And let's mark up what we know. So we know that this would be x0 and this would be 0y. And of course that's the origin. that's 0 degrees, and that's 90 degrees. So if I talk about the tan of 0 degrees, tan of 0, remember, is the y value over the x value. So at 0 degrees, the y value is 0, and the x value is x. Now, x is not going to be 0, so we can safely say that the answer of this will be 0. So the tan of 0 is no problem. But if we get to the tan of 90 degrees, we have a slightly different situation. At 90 degrees, tan is the y value over the x value. Now, what do we know if we're dividing by 0? We know that that is undefined. So we can never divide by 0. It makes the fraction undefined. And in actual fact, 0 is so small that if we divide it in, we get an incredibly big answer. So that's why we say it's undefined. So we know then, if we add on to what we had over here, the tan of 90 degrees is undefined. Now, what's interesting about that is later on when you get to draw the functions of sine, cos, and tan, you will see that at 90 degrees you get something called an asymptote. Just remember that, and when you come across that, you will realize why that happens, because we can't have a value at 90 degrees for tan. Okay, then a nice little summary of all your special angles can be found in this little grid over here. I know some people prefer to learn that. I quite like working with the triangles or working with the circle, the fan-like section. But you've been taught the triangles already on the last session, and so you can see for yourself what that is, but you can see this is a nice way to remember it. You could have the summary handy or just learn it off by heart and put it down and work with it. But it's interesting here, 1 over root 2. It depends which method you were using. If you're using the triangles, you will get 1 over root 2. But if you were using the fan method, which your teachers might have shown you, the fan method basically looks like this. I'll just show you in case you've seen it. And it shows a whole lot of coordinates. I'm not going to get into it because you have been taught the other one. But when you work with this method and you work with 45, you will get a different version of cos 45. You would get it as root 2 over 2. Now, don't worry about that. It's absolutely fine to write it as 1 over root 2 and then make the adjustment later on in your working. Or if you're using the other way, it is the same number. So if you're using either one, they're both correct. Right, let's go on to an example. All right, the example says we have a coordinate P with coordinates 3, 4. It is a point on the Cartesian plane, XOP. Sorry, my little angle there just sort of got sidetracked a little bit, so let's cross him out. So XOP is equal to theta. So X, O being the origin, P being there, there's my angle. And they called it theta, not A, so let's just rectify that. Of course, usually we use Greek letters when we're defining angles, but it's not the end of the world if you use capitals. Right, when X is the positive point on the X-axis without using a calculator, very important. When they say without using a calculator, you must be very careful to not use it. Because any sign that you have used a calculator means that you would get nothing for the question. So if it says without a calculator, please be conscious of that and try to avoid using it. Right, so they want us to work out the cos of theta. Now remember what they said to me. They told me the coordinate P was 3, 4. So in actual fact, what they've given me is the x value is 3, the y value is 4, because you agree all coordinates of the form x, y. All we have to do is find the radius, which we can do using Pythagoras' theorem. So Pythagoras' theorem says that x squared plus y squared is r squared. So the x is 3 squared, the y is 4 squared, and it's equal to r squared, which means 9 plus 16 is r squared, which means r squared is 25. Now r is equal to, and remember it's a radius, so it won't be negative, it'll be equal to 5. If I gave you x squared equals 25 and asked you to solve, you would then say x is plus or minus 5. And that would depend which quadrant we're in. But with radius, it's always positive. So I'm stressing that again, so you remember that. That's why I just happily disregard the negative possibility. Right, so now we know that the radius is equal to 5. You can also remember that there are Pythagorean triples. And the most common one is 3, 4, 5. And then there's also 6, 8, and 10. And of course, any multiple of that one would be applicable. And then there is 5, 12, and 13. These triples are useful. There are many others, but these 3 are the main ones that seem to get used in questions. So you know as a check that if you've got 3 and 4 for x and y, you've got to end up with a radius of 5. Obviously, if your x was 5 and your y was 3, then your radius would not be 4, obviously, because that would be different. But if the x and y values are the first 2 numbers here, then the radius will always come out as that. If you know the radius and one of these, the missing one's one of those. But you'll see me use it quite a few times while we go through the work. Right, so now we go to the cos of theta, and we know that the cos of theta is the x value over the r. So the x value was 3, and the radius was 5. So the answer is 3/5. And 3/5 is a perfectly respectable number. They said without a calculator, so I think that's fine. I suppose if you really wanted, you could write it as 0.6 as a decimal, but they didn't say that. They said without a calculator, so just leave it at that. Right, so let's see what the next question brings. It's still continuing on this previous one. It says there's still same coordinates. So I'm just going to quickly jot it down. There's my theta. There's my coordinates 3, 4. And my radius worked out to be 5. Okay, now they want me to find 3 tan theta. Well, that's not going to be a problem. What do we know about tan? Tan, by definition, is the y value over the x value. So it's going to become 3 times, and I like to use brackets for that. And tan, remember, is the y value over the x value, so it's going to be 4 over 3. Now, the good news is that that would be 3 over 1. So we can take that 3 and divide into that 3 once, and our answer will be 4. So it's a nice little answer for that one. So quite straightforward, nothing really demanding, except now we're still in the first quad, so we could have just as well been working with triangles. Obviously, I'm not going to stay in the first quad, because this is the whole purpose of having us able to move around. Right, so let's move to the next part, which is again the same question, but this time they ask for a half cosec theta. So let's get a drawing again. I'm going to be an expert at drawing this, but it's fine. It's 3, 4, and the radius was 5. That was my theta. There's my x-axis. There's my y-axis. Right, so over here we have a half. Now, cosec is the reciprocal of sine. So it's going to be r over y. So the radius is 5, and the y value is 4. Now we can see this one's not going to give us a nice little cancel down answer like the previous one did, but there's nothing wrong with what we're doing. So we look, we see we cannot cancel anything. So the rule of fractions says we times the tops together and we times the bottoms together. So the answer is 5/8. Now you see I'm not using my calculator at all. It is possible to do these things with a calculator, but when they say no calculator, please take cognizance of that and don't use it. Right, let's have a look at question 2. If we look at it, it says angle XOK is theta. It is an angle in the third quadrant. So, okay, that helps us a bit. That's your first quadrant, your second quadrant, your third quadrant. So they're telling me it's here. Okay, X is over here, the positive x-axis. So XOK would look like this, where K is down here. Now I'm going to draw a nicer picture of that. I just wanted to make sense of this with you so you could understand where I was getting it from. So let's start by drawing a nice axis. We know where we're supposed to be. We know how it's supposed to look. And let's have a look at this. So what I'm doing is I'm putting this angle in the third quadrant. The angle I'm referring to is this angle here, and that is my theta. This is X, that is O, and that is K. So K is a coordinate, and we can go and pop it in quite easily because they tell us that K is the point minus 5y. In fact, let's just make it a little clearer there. I don't want to squish it in so that you can see what you're doing. It's the coordinate minus 5y. That's your K. Now, what do we know? We know that OK is 13 units. So we know the radius is 13. What we need to do is to find the value of y, which is this coordinate over here. Now already, I'm hoping you remember the previous example where I talked about the Pythagorean triples. And I used the triple 5, 12, 13. So you can see you've got a 13 and you've got a 5, although it's a negative 5. So I anticipate the y value being 12 or minus 12. So let's talk about how we're going to get it using our sound methods. So our sound methods is we basically say to ourselves, okay, this is a kind of right angle triangle. We know that the x value would have been minus 5. The y value is what I'm looking for, so I know that x squared plus y squared is r squared. So the x is minus 5 squared. The y value we're looking for, and the r value is 13 squared. Right, so let's carry on working. That's going to be 25 plus y squared equals 169. Now, just at this point, I want to stop for 2 seconds and mention to you that although the question would have said without a calculator, if you checked your arithmetic that minus 5 times minus 5 is 25, for example, or 13 times 13 is 169, that would not be unacceptable. They wouldn't suspect that you had used a calculator because that's the kind of bonds you should know from primary school. But I know a lot of us get rusty on these things, so it's actually worth just checking it and not making a mistake with the arithmetic. But they wouldn't consider that a problem as long as you showed every single step. Right, so what do we know then? We know that y squared is equal to 169 minus 25, and so y squared is equal to 144. Now, if y squared equals 144, we are effectively using the difference of squares, so we know that y will equal plus or minus 12. Now, this is where the drawing is extremely important, because at this stage, I look at it and I say, there's my y. What do I know about this y? Well, it's going to be read off this part of the axis, which means the y value had to be negative. So if the possibilities are plus or minus 12, because of where the line is drawn, it must actually be a negative 12. So this coordinate now becomes minus 5, minus 12. So what I would do, I'd say, therefore, the y is minus 12. And if you want to give a reason, you can say third quad. If you want to. I don't think it's necessary. I think it's fine to just go there. So now we've established our y value, we knew our x value, and we knew our radius. So we actually have enough to be able to work out absolutely anything on this drawing. So let's go across to the second part of the question. It's the same question as before. I'm just going to jot this in quickly because we're going to need to use the values. It was minus 5, minus 12, and the radius was 13. This was my angle theta. That was K, that was O, and that was X. Oops. I think I've just picked it, selected it instead of wrote on it. Okay. Now it says prove that tan squared theta plus 1 equals sec squared theta. Now the moment you see the word prove, that means you've got to work with one side and make that one side become the other side. So if I look at this, I've got tan squared theta plus 1. That is my left-hand side of the equation. So that would be my left-hand side, and this would be my right-hand side of the equation. So by definition, we know that tan is y over x. So it will be minus 12 over minus 5, and I've got to square that, plus 1. So what we're going to do is we're going to work that out. Of course, a negative over a negative makes a positive, so we actually have 12 over 5 all squared plus 1. Well, 12 squared is going to be 144 over 25 plus 1. And then to get that as one fraction, we would take a common denominator of 25, realizing that's over 1. So it's 144 plus, well, 1 goes into 25 times. 25 times 1 is 25. So we're going to get 169 over 25. Now, if we get the same answer for the right-hand side, then in actual fact, we've managed to prove the left side equal to the right side. So let's go up to the question again. And now we're going to work with our right-hand side. So I'm going to change the color pen so it's clear where I'm working with which one. So on the right-hand side, we have sec squared theta. Now, sec by definition is the reciprocal of cos, so it'll be r over x. So the r value was 13, and the x value is minus 5, and we have to square it. So a negative squared makes a positive, but you could do it individually, so we could say 13 times 13 is 169, And minus 5 times minus 5 is going to be plus 25. And the moment we do that, we see, hang on a moment, look at that. The left-hand side equals the right-hand side. And therefore, we can conclude that tan squared theta plus 1 is equal to sec squared theta. And that's the end of it. Now, just very clearly how I set it out. Left-hand side equals, right-hand side equals conclusion, left-hand side equals right-hand side, and the statement written down. That's just nice for someone marking your paper that can follow your logic clearly and figure out what you're doing. Right, we're about to go to ad break, and we will see you after that for the next examples. Hi, welcome back from the break. Let's have a look at another example. We've got two really nice examples here. The first one we're going to start with is this one, which says if sine theta equals 0,4 and theta is an obtuse angle, we'll talk about that in a moment, determine cos theta. Now, before we even start working with it, I just want to mention a few things. I'm sure this question, if it had been set, would have said without a calculator. Why? Well, first of all, they've told you sine theta is a decimal, and of course we all know decimals can become fractions, so it's going to be no problem to make something out of it. But more interestingly, they're asking you for the cos of theta. If they'd asked you to find theta, then I would have suspected you had to use a calculator and work out the angle and et cetera, which I believe you did in your last session. So right, let's go over here then and talk about how we approach this question. Right, first of all, they tell me that sine theta equals 0,4. Now, what I would like to say to you here is we know that sine, by definition, is y over r. And if we are going to work without a calculator, it would be best to write that 0,4 as a fraction. That way we could say y is, r is. But just beware there, because there are many ways to get 0,4, not only one way. So one of the immediate things I'm sure you're all thinking is to say to yourself that it's 4 over 10, which is absolutely fine. Now, if it's 4 over 10, I'm saying that the y value would be 4 and the radius would be 10. But it could have just as well have been 2 over 5, and that 2 over 5 would have still given me 0,4. So it would have been y is 2 and r is 5. Now, you might be saying to yourself, but hang on, that's confusing. Don't worry, because in actual fact, if you had to plot these points, it'll work out. They'll all lie on the same arm. So the same radius. When I draw it just now, I'll tell you what I mean by that. Of course, you could have also written it as 40 over 100, or any other version you feel like. But I think for the purposes of this question, I'm going to work with 2 over 5. So I'm going to work with sine theta equals 2 over 5. Just because working with smaller numbers is always easier than working with bigger numbers, and so it's all good. Now, what did I highlight obtuse for? Well, we know that if angles are acute, we're talking about something like that, where this would be the angle. Obtuse means more than 90 but less than 180. So it would lie like this. And the angle we'd be talking about would be this one here. So if that's the case, which quadrant will we be in? Well, I know you've already got that answer, so let's draw a picture and have a look at it. So let's draw in our axis, and I see I've managed to put an extra little arrow over there, so let's just get rid of it. Okay. And from what I showed you now, I'm sure you can see that this would have had to be your theta, where that's x, O, and let's call this point P, for lack of a better name. Okay, so is that angle obtuse? Yes, it's more than 90 degrees, but less than 180 degrees. Now, the moment we're in that quadrant, what do we know about our x, y's, and r's? Well, in that quadrant, what do we know about the x? Is it positive or negative? Well, I know you all got this idea already, so you are saying to me it's negative. The y is positive, and the radius, remember, is always positive. So if we go back to this, the y value we said will be positive, so it's going to be 2 here. We want to find the x value, and we know that the radius is 5. Okay, so if we were working with a 4 over 10, we would have just named it a little bit differently, but basically it would have been the same kind of idea. Right, so now if we look at this, we are looking for the x value. So from Pythagoras' theorem, we know that x squared plus y squared, which is the 2 squared, is equal to the r squared. And of course, hopefully you were thinking Pythagorean triples, because remember I warned you to watch out for them. But you can see that the one we have is 3, 4, 5. The 5's there, but we don't have a 2 there. So the triple will not work for us. That's fine, no problem at all. Let's get rid of that because we don't need that. So we're going to work with this normally. So we're going to say x squared plus 4 is equal to 25, which means x squared is equal to 25 minus 4, which is 21. Okay, maybe I should show that step. I think we should show it. Eh? Let's not leave out any steps. So it's 25 minus 4, which means x squared is 21. Now remember, we decided from our drawing earlier on that the x value would be negative. And remember what I said to you right in the beginning. I said if we're looking at r squared equals 25, then we know the answers are going to be r is going to be 5 because radius is always positive. And I said to you, if we've got x squared equals 25, well then we can get plus or minus 5. And depending which quadrant it is in, we will decide whether it's positive or negative. Well, this is the case I was mentioning. So let's have a look at what we've got. So we know that x is equal to either plus or minus the root of 21. Now, in terms of our drawing and where it's drawn, we have already established that this x value would have to be a negative. So my point P would be negative root 21, 2, and my radius, of course, is 5. So the first bit has taken quite a while to work out, but it's fine. We now got the x, y, and r, and after this, the question becomes easy. Because once you've established what everything is, our check was it's obtuse. That means that the x value is negative, and we know it's drawn in the second quad. Those are important facts, and if it was a test or an exam, they were giving you a mark for drawing it in the correct quadrant, a mark for getting the correct x value, the negative. Right, so now we go to the question which asks for the cos of theta. Now we know that cos by definition is our x value over our r. So the x value is minus root 21 over our radius, which is 5. And so that would be the end of that question. They said without a calculator, or as I said, they should have said without a calculator, so we would leave it there. Right, now let's go to the second part of the question. I need to remember those values, so I'm just going to jot a little drawing down here, so we've got it for future reference. We found P to be the coordinate minus root 21, 2, and the radius was 5. Right, now they're asking me, and remember that is my theta here. It's always good to show your angle on your drawing, so it's clear. Now they're asking me for root 21 times tan theta. Now, tan theta by definition is y over x. So if it's y over x, we're going to go over here and we're going to say root 21 multiplied by, and I like to use a bracket, the y over the x would be 2 over minus root 21. Now that's quite nice because we know that we can make this over 1, and we can see that that root 21 divides into that root 21, and so my answer is 2 over negative 1, or if you like, minus 2. So there we have the answer of the second one. Again, quite straightforward. They often do this with the root sign, that you can actually cancel it out. Sometimes they mean and leave it in, but mostly it cancels out or becomes a denominator or something that makes the arithmetic a little bit easier. Let's go to question 4, and it's a little bit different this time. Now, teachers are always debating how can they make sure that when they give you a question you can't use your calculator. Well, this is an example of where we can make sure you do not use your calculator, because what we do is we use variables instead of numbers in the question, and that makes it a little bit more exciting. So right, it says given that tan theta equals t over 2, where theta lies from 0 to 90, find the following in terms of t. So in other words, they're not asking you to get number values for this. They're asking you to express these answers with t's in them. So it's not a big deal. They've helped you out a lot. They've told you that theta lies from 0 to 90. And if that's so, which quadrant are we in? Well, clearly, if it's 0 to 90, we're in the first quad. So let's get a little picture. And I think this is the one I'm going to need to do the picture several times. But it's fine. We'll persist with it. Now, I know it's in the first quadrant. because they told me that. There's my theta. They're telling me that tan is t over 2. Remember, tan is the y value over the x value. So that means the coordinate here would be 2t. What do we know about that t value, even though it's not important within this question? We know that it's in the first quadrant, so therefore will it be plus or minus? Well, it's clearly going to be a positive. It's in the first quadrant. X, y, and r are positive. So we know that, but it's not important within the context of this question at all. Right, so now they want me to find the sec of theta. Now remember, sec by definition is r over x. Now, do we know our radius? No, we don't. So we need to find the radius, but it's not going to be difficult because we've got our best friend, Pythagoras. I always used to joke with my students and say, if I had my way, I would have married Pythagoras. And I'm sure if any of you have seen pictures of Pythagoras, you'll wonder how sane I am. But he was a very interesting man and very liberated because he let his wife go to school. So that was good for him. Right, so let's have a look and sort this out. So we're going to drop down a perpendicular effectively. We're going to say our x is 2, our y is t. Let's find our radius, which is this guy here. So r squared is equal to x squared plus y squared, which is 4 plus t squared. Now, if that's so, remember what I said to you about a radius? A radius is never negative. So when I square root this, I only need to take the positive square root of that number. So the root of that is going to be 4 plus t squared. Now, I'm standing by with bated breath because what a lot of students do is they forget their laws about square roots. So just for a few seconds, I'm going to stop and mention something. If I've got something like this, how would I work that out? I would say it is the square root of 20, which then, of course, would stop there. But it is not equal to 2 plus 4. Now, before we move off that, what have I done? I've actually square rooted the 4 and square rooted the 16 and then added them together to get 6. Do you agree with me that the answer of 6 would have had to come from 36 here? So let's use two numbers that are more familiar to you. Let's use 9 and 16. Now, if I use 9 and 16, it is the square root of 25, which means the answer is 5. It is not equal to 3 plus 4, which means it's not equal to 7. So you may not use the square root sign over addition. Okay, it's not allowed. So over here, that is as far as you go. You cannot do anything more, even though that's a perfect square, and even though that's a perfect square, you may not continue. You leave it just like that, and there's nothing wrong with that. It's perfectly acceptable and good. Let's get rid of that and go up here. Right, so as I said, we're dealing with sec, which is your r value, and your r value has worked out to be 4 plus t squared over your x, which is 2. And that's your answer. Nothing wrong with it. They said express it in terms of t. It's ugly, but it's not that ugly. Okay, so we know for a fact that's the answer. Now, again, if I move across to the next part of the question, I'm just going to make sure I get the rest of this written in, just so we've got a picture to refer to. So it's just a little rough sketch. It's 2 and t, and the radius works out to be the root of 4 plus t squared. This is my theta, x-axis, y-axis, origin. Right, now the next question says to me, find cot theta. Now remember, cot is the reciprocal of tan, and tan is y over x, so cot will be x over y. So we know we want the x value over the y value. So in terms of that, we're going to go here, and the x value is 2, and the y value is t. So that's all good, no problem with that at all. Right, so now we go to the next question, which now gets a little bit more exciting. They're introducing a square. So we're going to talk about that in a minute. Let's get the basic drawing up again. It's going to be 2 and t. The radius is the root of 4 plus t squared. Theta there, x-axis, origin, etc. That's good enough. Right, so now I want cos squared theta. Now what I need you to notice is that cos squared theta means cos theta times cos theta. And the way we write it is convenient. So there's nothing wrong with us doing this. and perhaps that makes it a little bit easier to work with. It's just a nice, easy way to write that square. It'll look ridiculous to put the square on the angle, and we never do that. We always put it on the ratio, but it in effect means the whole answer squared. Now we know that cos is our x value, which was 2, over our radius, which is the root of 4 plus t squared. And that I must square. So if I'm squaring, I times the top by itself, so 2 times 2 is 4. But what happens when I times a root by a root? Well, it's going to just actually effectively fall away. If you've done exponents, you would know this, that I could write a root like this. And if I times it by itself, the bases are the same, so I can add the exponent. So it'll become a half plus a half, which means it's 4 plus t squared. But an easier way to understand it is if I've got the root of 4 plus t squared times the root of 4 plus t squared, I can get that. And of course that's the same as saying 4 plus t squared squared, which means the answer is 4 plus t squared. So it's up to you, however you like to do it. We get that. And now it's another little spot that teachers just love to try and catch students on. And that is where they leave the temptation in the way for you to do this. Do you agree with me? We can't cancel the 4s. If I had 4 over 4 plus 6, do you agree with me? It would be completely incorrect to do that. And once again, it's because you may not cancel over a plus sign. So that is definitely not any temptation. That is how it should be, and that's where you'd stop. The actual answer of that would have been 4 over 10, which would have cancelled to 2 over 5. So it's definitely not what I want you to do, so just be aware of that. Teachers are inclined to ask questions like that because they test whether you are aware of these rules indirectly. So it's a nice way to ask it. Okay, let's go to the next part of the question, and you can see it gets a little bit more exciting because now they've got 2 squares. But it's no problem for you because you've already got the idea. So let's pop a drawing in here quickly with the values. It was 2 and t. The radius was the root of 4 plus t squared. There was my theta. Right, so if we look at this question, it says to me tan squared theta, but we know that that means tan theta all squared minus, and over here we've got sec squared theta, so it's sec theta all squared. Now, what we do know is we know what the tan of theta is. It's given to us. So we don't need to do anything with tan theta. It's already there. So don't waste time trying to work it out again. If it's in your question, just use it. So we go along here and we'd say that tan is t over 2 all squared. Now we did work out the sec of theta earlier, but I'm just going to use it again here. Remember, sec is your r value over your x value. So your r value is the root of 4 plus t squared over 2. And we've got to square it. Right, so now we go over here and we're going to square this thing. And it's just going to become t squared over 4, because that's nice and straightforward. But this one, just remember we've got the square root sign and we're squaring it. So if I have root 3 and I square it, it's going to be 3. Same here. I've got the root of 4 plus t squared, and I'm going to square it. So it's going to be 4 plus t squared over 4. Now, this is a lovely way for the teacher to ask you a little bit of algebra, which is great, because now you've got to simplify that fraction, and there's that negative there. So just be aware of it. So let's look at what we do now. So we put it over 4, and we say that'll be t squared minus, but remember, we must effectively bracket that, because that negative affects the entire value. Let's change to green. So it becomes t squared minus 4 minus t squared over 4. Now that's quite nice. How did I get that? Well, that was a 1, and I literally times the minus 1 in there and the minus 1 in there. That's how I got the minus 4 minus t squared. So now that will fall away with that, and I'm going to get minus 4 over 4, which means my answer is negative 1. Isn't that a lovely little question? Started off so mean looking, but look at the lovely answer you've got down the bottom there. I always enjoy questions that come out so beautifully. Right, so hopefully now you've got a very good idea on how to use these reciprocals and of course how to work with our cast diagram. And you can see it's not a huge stretch for you. It's a little bit further than what you needed to know before. And I'm sure you've got the idea and you are actually looking forward to doing questions on it. Yeah, thanks for joining us today from Learn Extra. We will speak to you soon again.